Okay, let's do the thing. All right, so I got to finish up one section from last lecture. So these are the lecture slides from last time for your reference. Then as soon as I get this done, we'll keep going onwards to today's content. Okay, that's the plan. Okay, so this is the second of many cryptography lectures. Last time we went through a bunch of definitions. And today the goal is to start with a couple of cryptographic schemes. Okay. So this is the roadmap you've seen before. We saw it last time. You'll see it over and over again. And so for almost all of today, we're going to be in this top left corner. And what it means to be in this top left corner, okay. So what it means to be in this top left corner is, well, we're using symmetric key. So that means that for all of today, we're going to assume that Alice and Bob, the people trying to communicate, they know a secret that nobody else knows. How they get that secret is not our concern for today. And the other thing about being in this top left quadrant is that we're dealing with only confidentiality today. So our goal is just to make sure attackers don't read our messages. And we are not so concerned about whether or not attackers can modify our messages. That'll be a later day. Okay, so that's our setting for today. So we'll get started with our very first scheme, which is one-time pads. So to tell you all about one-time pads, I have to give you a quick review of bitwise XOR, which you may or may not have seen from a previous class. So bitwise XOR takes in 2 bits. If it is a 0 or a 1, outputs a bit. Outputs 1 if the 2 bits are different, outputs 0 if they're the same. And here are some useful properties. Most of these, again, they either seem familiar or you can just prove them based on the definition of XOR. But there is one that's kind of handy that I'll call attention to down here, which is this one. So if I say X, XOR Y, XOR X, turns out the 2 X's, they cancel. So we see it that X XOR with X is 0. And so this ends up being Y. So this last property is kind of handy. If you're not convinced, you don't have to believe me. You can prove it yourself by using the definition of XOR on the left. But those are the properties we're going to see a couple times today. So good to have them in mind. Okay. Something else pretty cool about XORs is that you can do algebra on them. And again, you don't have to believe me. You can go and try this yourself on some examples, and you'll see that this always holds. But something pretty cool is if you have some expression with XORs and you want to solve, you can actually XOR both sides and the equality still holds. So if I XOR both sides by 1, this equation still holds. And I know, thanks to my handy property from before, that if I have 1 XOR 1, it cancels out. And on the left-hand side, I'm just left with Y. And on the right-hand side, I'm left with 0 XOR 1, which is 1. Okay. So hopefully not boring you too much if this is all review, but that's the XOR algebra you have to know for this unit at least. Okay. Great, so here's our one-time pad scheme. It's our very first scheme. And remember, for all of our schemes, we have to decide a couple things. So one thing we have to decide is, what is that secret key? What's the secret value that Alice and Bob both know? Well, we said that in the symmetric key setting, we're going to interpret everything, the key, the messages, everything as 1s and 0s. And I don't know, maybe it's an image, but we can always interpret the image as some sequence of 1s and 0s. So the secret that Alice knows, there it is. It's sitting right in front of us. It's that sequence of 1s and 0s. How was it chosen? For today, we'll say it was chosen randomly. Alice and Bob both know it. Okay, great. So Alice and Bob both know this key. How was it generated? We flipped a coin. Okay, it came up head, so we said this is 0. We flipped it again. It came up tail, so we said 1. We did it over and over again. We got this long string of 0 and 1s. That's totally random. Could have been anything. Okay. Next, we have to come up with, how do you encrypt messages? I have a key. I'm given a message. How do I scramble up that message using the key to produce the ciphertext? That's our encryption algorithm. So let's do it. Here's the message. There's the key. And you can imagine there's so many different things you can do here to combine these two and output something. Some of them are secure, some of them aren't. Here's what one-time pad decides to do. So we decide, remember that like XOR thing that you just saw? That's pretty useful. So let's use that to scramble up the bits. So we're going to do an XOR on every single one of the bits, one by one. So the first bit of M XOR with the first bit of K, that's the first bit of your output ciphertext. Do it again for the second bit and the third bit. And every bit gets an independent XOR. And our result is this ciphertext out here. It's totally scrambled up. Okay, great. We have our encryption scheme. Now let's come up with our decryption scheme. So remember that in our setting, in the story between Alice and Bob, Alice now takes this ciphertext, sends it over to Bob over an insecure channel, which means that other people, including the attacker, they can see this value of C. And now it's up to Bob to decrypt it. So let's see if that works. Okay, so what does Bob have? Bob knows the key. Whenever you're thinking of cryptography, sometimes when these schemes get really complicated, one thing that always helps is to think, what values do you know, but what values do you not know? Especially if there are a lot more symbols than just K and C and M, you might have to start thinking to yourself, what does Bob know? In this case, Bob knows K. Why? Because K is that secret symmetric key that Alice and Bob both know. Bob also knows C. Why? Because Alice passed it over to Bob over the insecure channel. So Bob knows both of these values. That's great. What does Bob not know? Bob doesn't know M. M was sent by Alice. So we have to figure out as Bob, what's the value of M? So let's do it. So I'm going to propose, and I haven't proven it to you, I'm going to propose that the decryption algorithm is to do another XOR. So take K, XOR it with C, and do it for every single bit. And the result, I'm going to claim is M. I haven't proven it, but that's what we're going to try. Okay. And people with really good memories might remember that this was the value of M, 1001 something something. And it does seem at least that when I decrypted, I got the same value back. So at least in this case, it worked, but I haven't proven it to you. How do we know this is gonna always work? So let's go through this scheme in more detail now that we've seen what it looks like, and let's try to prove some properties about it. Is it always gonna work? Is it secure? Can Eve learn something about the message? So here it is in text. I'm gonna go through it in all the gory detail, but we generate the random key, and to encrypt, we do a bitwise XOR on every single bit of M. And to decrypt, we do a bitwise XOR with K and every single bit of C, the ciphertext that you receive. Okay. A couple of things I will highlight here are that we're going to assume, at least for today, that the message is the same length as the key. And also that every single time you encrypt a new message, you're going to come up with a new key. That's what the rules of this scheme say. If you have different schemes, they could have different rules. But the rules for this scheme say for every new message you encrypt, you got to come up with a new key. Alice and Bob have to know that new key. And the key is the same length as the message. That's how the bitwise XOR works out. Okay. So now let's prove things about it. Well, one thing we'd like to prove is, like, does it actually work? We saw in the example, we got the message back, but how do we know that always works? So here's the algebra for it. So what do we say? We know this thing. How do I know this? Like, what's justifying this line of algebra? Well, that's the definition we had from earlier. How do you encrypt something? You XOR the key with a message bit by bit. Okay. What happens when you decrypt something? Well, this is the definition of decryption, right? So Bob takes K, which he knows. He takes in this thing, which is the value that Alice gave to Bob. That's C, right? And well, what do we know about decryption? We know that decryption is just XORing this thing with this thing. So let's do it. Okay. I guess before we do that, we can take this encryption. We know what it is. It's K XOR M. So we plug it in. Okay. And then now we know the definition of decryption is just XORing the first argument with the second argument. So we do that. And then using that little handy XOR property that I told you about 5 minutes ago, the K's cancel out and we get M. So we prove that it doesn't have to be that message I chose on the previous slides. Any message M that you pass in is good to go. When you encrypt it and you decrypt it, you get the original thing back. Intuitively, all of this proof, it's just saying that the K's cancel out. So encrypt, you XOR with K, decrypt, you XOR with K again, K's cancel out. Okay, great. So we know that it works. Now the question is, when Alice takes this ciphertext that's all XORed up with K and we send it across the channel, what can Eve learn? Can Eve learn anything about it? Well, let's find out. And we know our definition from last time, which is that someone who sees the ciphertext should not learn any more information that they didn't know previously. So we even designed an experiment or a game to test this out. So let's try that out. So this was our experiment. It's not going to exactly work in one-time pads, and I'll explain why a little bit more later. But let's take this version of the experiment that you're seeing on the slide, and let's play the same game using the one-time pad, and let's see what happens. So we know, so I guess, let's see, I guess you will be Eve and I'll be Alice, just like last time. Okay, so you're Eve and you have chosen two messages, M0 and M1, and you've presented them to me. And you know that I've turned behind you, I flipped a coin, and then I encrypted either M0 or M1, and I sent it back to you, okay? And you don't know which one I sent. So it's your job to guess. So I'm showing you the ciphertext C, and I'm telling you I either encrypted M0 or I encrypted M1, but you don't know which one. And it's your job to figure out which one. And you can do anything at your disposal. So do whatever strategy you feel like, try to figure out what I encrypted, and then take a guess. And we can play this game over and over and over again. And anytime you guess right, you win. And so if you win more than half the time, that means that I must be leaking some information, because that C that I'm giving you, it must be giving you some clue as to whether I'm picking M0 or M1 to encrypt. That's how you're winning with probability greater than a half. But if I keep giving things to you and your win probability just cannot exceed a half, that means, what are you doing? You're basically guessing. You have no idea which one I'm sending. You're guessing every single time. That's why your win probability is a half and no greater. So if you are, as Eve, win with probability a half and no greater, then I think this scheme is confidential, because you have no idea what you're doing for any Eve out there. But if you're able to come up with some strategy that lets you win more often, that means that you must have broken something about my scheme. So my scheme, this one-time pad, probably not confidential. So let's write out this game in some math. This is the experiment. The experiment is, you told me M0 and M1. I turned around, I flipped a coin, and I sent you back one of these two things, either this or this. So there are two possible worlds that we have split into. There's one possibility where we're in the world where you got this value and you're looking at it right now. There's another world in which you got this value and you're looking at it right now. And you don't know which world you're in, and it's your job to figure out which of these things actually happened. It's not both. It's not like we did both of these things. Only one of these two things happened. You got to figure out which one. So let's think about, in expressions, what exactly happens in each of these worlds. So in, like, multiverse number 0, if the message that I encrypted was M0, then you received this value, okay? And if we do a little bit of rearranging using XOR algebra, then we can actually derive an expression for K. That's pretty cool. So that means that you, as Eve, you know C. Why do you know C? Because I've supplied it to you. And you know M0. Why do you know M0? Because you told it to me, remember? And so if you know both of these values, then you can actually derive what you think K is. That's pretty useful. So if you know that you're in world number 0, you can take the C that I've given to you and the M0 that you've given to me, and you can come up with your guess as to what that secret K is that I'm using. You don't know the K that I'm using, but according to this, you might be able to derive it. What about the other world? Because this is not the only world in which you can be in. You might also be in this world. And in this world, things are basically the same, but instead of M0, I encrypted M1. You can play the same game or do the same strategy of, you know C, I told it to you. You know M1, you chose it and gave it to me. So if you XOR those values together, that's your guess for K. Okay. And you can compute this. In fact, you can compute both of these. You know C, you don't know which one it is it that one or that one? But whichever one it is, you can XOR it with M0 and you can XOR it with M1. You can get two guesses for K. That's great. So as the attacker, you can see, well, K could be this thing or it could be this thing. And so now your strategy is, which of those Ks was it? Can you tell? Well, K was chosen randomly. So you look at these two Ks and I ask you, which one is the real K? You're like, I don't know. K was just a bunch of random coin tosses, random ones and zeros. So even though you were able to come up with the two possible values of K, you have no idea which is the right one. Why? Because I chose K totally at random. So both of these are equally likely in the space of all the possible Ks out there in the world. Okay, so all of this proof boils down to the fact that there's two possible worlds. In both possible worlds, you can come up with a guess for what K is. However, once you do come up with that guess, you have no idea which K is more likely, because K is just a random sequence of coin tosses. So this strategy, it doesn't help me at all with a one-time pad. And so if you tried this strategy, no matter what you do, sorry, no matter what you do, turns out you're just going to be guessing with random probability, because even if you come up with these two expressions for K, you have no idea which one is more likely than the other. So you just have to guess 0 or 1, and the odds of you guessing correctly, 50%. It's like a random coin toss. Okay, so that's our rough sketch of a proof. This is not a totally rigorous proof. For this to be rigorous, we would have to explain why other strategies out there don't work. But this is one possible strategy that you could use. We've shown that it doesn't give you any extra information. And if you extend this proof sketch a bit, what you'll notice is that the one-time pad, if we use it correctly, it doesn't leak any information. So we used our experiment to prove to ourselves, or at least give ourselves a sketch of a proof that no matter which world you're in, or if I tell you that you're in one of these two worlds, the M0 world or the M1 world, you have absolutely no idea which is which. You know, you can go home, try out other strategies to come up with which world you're in. It's not going to happen. You're not going to come up with something that's going to help you with greater than 1/2 probability. Okay. That's the one-time pad. It's wonderful. Like, look, it says perfectly secure. So why don't we just go home right now? Well, there is one problem, which is, remember how we said Alice and Bob have to use a different key every time they encrypt? That's kind of annoying. I don't like that, because now Alice and Bob have to figure out a whole bunch of different keys, and that's kind of annoying. So we'll talk about why it's annoying in a bit. But one possibility is to say, well, why bother with a bunch of different keys? Why not just use the same key on the second attempt or on my second encryption? So let's do that. So in this case, I've got two messages, and this time we're not playing the game. So when we say M0 and M1, it's not to plug it into this experiment. I'm just reasoning about what happens if I take a message and I encrypt it twice with the same key. So let's try it. Alice takes a message, any old message, uses the same key, encrypts it. We know the encryption algorithm is that bitwise XOR, and we get this thing as the output. And remember, the output of the encryption, that's the ciphertext. That's something that Eve sees. So Eve can see everything outside this Alice box, including this value. Okay, so Eve observes this value. Okay, fair enough. And then sometime later, Alice is like, you know what? I have something else I want to send to Bob. So I'm going to take that something else. I'm going to encrypt it. But instead of following the rules and using a brand new key, like this probably should have been, K2 or something. But instead of using a brand new key, Alice says, you know what? I'm kind of lazy. I'm just going to use that same key that I used last time, and I'm going to feed it into the same encryption algorithm. I'm going to get K XOR M1. And Alice is going to send this over to Bob. So in other words, Eve, as the person observing the insecure channel, sees these two values. Okay. Well, these values by themselves, maybe they don't tell me anything about M. And we saw before that if only one of these was sent, just knowing K XOR M0 tells you nothing at all about M. But what if I see both of these values? Well, what can I do? Well, now there's lots of things you can do. So you can try and ponder and think, if Eve has these two values available to her, can she learn anything about M0 and M1? Can she, remember, confidentiality is the property that Eve can learn nothing. So if she learns anything at all about these messages, then we're in some trouble. So what could Eve do? Well, you could think about it and ponder. Here's one possible thing Eve can do. Eve could take these two ciphertexts and she could XOR them together, right? That's a sequence of ones and zeros, and so is that one. So I can perform a bitwise XOR, and if I do that, I get this expression, which is the bitwise XOR of those two things. Remember our handy little XOR properties, or something XOR with itself cancels out. And why I learned this thing? So somehow Eve is able to compute M0 XOR M1. Is that useful? Yeah, it's pretty useful, because now Eve knows whether 2 bits of M0 and M1 are the same or different. That's pretty useful. And okay. So it turns out if you use 2-time pads, you learn something about the message. You learn which of the bits of the two messages are the same and which of the 2 bits of the messages are different. And depending on what the messages are, sometimes that can actually give you a lot of information. But even if it doesn't give you a lot of information, the fact that it gives you some information, namely which bits of the messages are the same and which bits of the messages are different, that alone already tells us that this 2-time pad scheme where I reuse the key, not secure, because Eve learned something. If I wanted to formalize this, I could play the NCPA game from before. I run the experiment. We have Eve send messages. Or we have Alice encrypt one. I could go through the whole game and show you through that proof that this scheme doesn't work and it's leaking information. But intuitively, I can also work it out just by noting that, hey, as an attacker, there is a strategy to learn something that's not trivial about the messages. And so that's another way to show that this thing is not secure. Okay, great. And if you are curious why it is that this is not secure, you can even imagine that if Eve learns one message, she can guess the other. And if she learns the other message, she can guess the first one. That's pretty bad. Okay. So takeaway from this section is that if you reuse the same key twice, a lot of things break. So we can't do that. We have to use a different key every single time. Is that easy? Well, not really. And so even though we haven't told you how Alice and Bob share a secret, it turns out that takes some time. So if Alice and Bob have to come up with a different secret every single time, that's kind of expensive. We don't really have time for that. That's the first problem. The second problem is like, think about what's happening in this case. If Alice and Bob want to know a brand new n-bit secret key, right? Or I guess let's start with Alice and Bob want to know a secret n-bit message. So Alice has a message, it's n bits long. She wants to send it to Bob. Okay. And so before I can send the n-bit message, what do I have to do first? Alice and Bob first have to figure out and agree upon an n-bit key, which means that Alice and Bob somehow have to secretly communicate n bits of the key between each other. And so if you're already going through the trouble of communicating the n-bit key, why not just communicate the n-bit message at that point? And so this seems a little bit silly, right? If I have to figure out an n-bit key before I can send an n-bit message, well then, why not just do the thing I did to send the n-bit key and just stick the message in there instead, right? So we'll talk about this a bit more as we talk about key distributions and how to agree upon keys. But the idea is just, this takes too much time. Having to come up with a new key over and over and over again, every single time I want to come up with a message is just too expensive. Okay, the only time where this might work is maybe Alice and Bob are hanging out in person and they're like, hey, I have some keys, you have some keys, let's share them while we're in person and we have a secure channel between ourselves for now. And then once we go our separate ways, maybe we'll use the keys later. But that's pretty rare. In real life, that kind of never happens. So turns out one-time pads, it's a nice idea. We saw some applications of the security proofs and how to see if they're secure or not. But like in reality, people just don't use this because that idea of having to generate a new key every single time, it's way too slow. Okay. So I mean, the only times people use this are like in those old-timey spy movies. I'm not going to talk about it in too much detail for now. But I mean, yeah, it's not something that people use, at least with computers these days. Okay. But apparently it was used in like, World War II, Cold War era. So if you're curious about that, there's a slide about it. I'm not going to talk about it in too much detail, but that's one-time pads. So we saw that if you use a different key every time, we can show that the attacker can't learn anything about the message if they only see the ciphertext. However, we also saw that if you reuse the keys, then a lot of things go wrong. And finally, we saw that if you do reuse the keys, then it's really hard to come up with, or like this scheme is really hard to use. Okay. That's it from the last lecture. Anything else you want to know about one-time paths before I abandon this and go to the current lecture? Question was, why not try XORing both possible Ks with C and see if either one gives you a message back? Okay, so the suggestion was to go back to this strategy. I'm going to go through it in too much detail right now. But the suggestion was, well, maybe what I can do is I can take the ciphertext, I can try and decrypt it with both of these keys that I came up with and see if one of the messages came out. Yeah, I'll think about it some more. But in theory, the idea here is that those two keys are both equally likely. At least that's what this slide says. And so because I don't know which key is more likely than the other, the scheme is secure. But I'll come back and think about that some more at the end. It's a good question. Okay. If that didn't make sense, don't worry about it. It's a question on Zoom. Okay. All right, so let's talk about block ciphers, which will fix our problem from earlier, and we'll start building our way toward schemes that are used in practice. Okay, so I won't go over the summary in too much detail, but it's there if you want it. Let's talk about block ciphers. We're still in the same square as before, because one-time pads, it did not achieve our goal of giving us confidentiality in a practical way. So we're stuck in the same square. We got to finish up the square, and then we can move on to some of the other ones. All right. So to do that, I'm going to introduce a new type of function. It's going to look kind of similar to the previous one, but we'll see how this is implemented and how we can use it as a building block for later. Okay, so I'm going to walk you through some math, and then we'll talk about what this thing actually means. Okay, this thing is called the block cipher. So the block cipher is the algorithm here. You can imagine that like living in this block, it's some piece of code that's going to do something to all the bits and shuffle them around and manipulate them in some way. Here's how you define a block cipher. I haven't told you what's going on inside the box. There's many different types of block ciphers, but every type of block cipher has to follow this definition that you see on the slide. So every block cipher has an encryption algorithm and a decryption algorithm. That should feel pretty familiar. And in both cases, when you encrypt something, what do? You take in a key, you take in a plain text, and you output a ciphertext, just like we saw from before. Okay, the thing that's a little bit different from our one-time paths from before, well, a couple of differences are this thing living in this E box, it doesn't have to be XOR, it can be something else. And we'll talk about what those other things are. But let's think about the inputs. So this thing is going to be K bits long, and the plain text is going to be N bits long. Both of these are a fixed number. So once you choose the value of K and the value of N for your specific algorithm, they can't change. So I could say the code living in this E box is some algorithm that works for 128-bit plain text and 128-bit keys or whatever. And once you pick those sizes, they are fixed. So block ciphers are for a fixed size plain text and a fixed size key, even though on the slide I said K and N. Okay. And what's the output? The output is a ciphertext of length N bits. So if you pass in plain text of N bits, you get ciphertext output of N bits. Okay. And what about decryption? It kind of looks the same. You pass in a key, it's a fixed length, K bits, no changing it once you pick K. Pass in an N-bit ciphertext, get out an N-bit plain text. Okay, should feel pretty familiar. And so this is a general class of functions. And just like before, there are some properties we want, but this is not just a specific function like the XOR. This is a whole class of functions. And so anything that you can possibly think of that goes in the E box or the D box, could be XOR, could be things that are more complicated. They should have some certain properties. So one of the properties is that, well, it better be correct. And so if you encrypt something and then decrypt it back, you'd better get the same thing. And we'll talk about how making E sub k a permutation is a fancy way of ensuring that when you encrypt something and decrypt it, you get it back. Second thing I will note is that we'd also like this thing to be fast. And we'll talk about fast in a bit more detail. We're not going to be too rigorous about it. But the point is, in this E, you better not be doing something that's like horribly slow, because we want this to build, or we want to build block ciphers and algorithms that are reasonable for people to use in practice. So just in the back of our heads, efficiency is a nice thing to have, even though we won't like prove it. Okay. And the last thing is, how do you prove that this thing is secure? Living in this E is some algorithm, and we don't know what it does. We'll show you some specific examples. But the goal is whatever you place in that E or that D box, whatever shuffling of bits you choose to do in there, it has to behave like a random permutation. What the heck does that mean? I'll show it to you in a couple slides, so stay tuned. But those are the properties that we want, and this is the general picture of all the schemes that we're about to see. Okay, let's do it. So another way of thinking of these schemes is, well, as we said from before, we don't want to change keys all the time because we already know that coming up with different keys over and over is slow, it's a waste of time, it's not practical. So another way of thinking of this E sub k of M function, right? You're like, wait, why not write this the way that I wrote it from before? Before I kept writing E of k comma M. But another way of thinking of E, and this is kind of weird, and even when I saw it the first time, it took me a bit to wrap my head around it. So another way of thinking of E is that E is like a whole family of functions, okay? And so there's a whole family of functions. For example, there is E of 0 comma M, okay? And once you fix k equals 0, this is now a function that maps an n-bit input to an n-bit output. Why is that the case? Because you've already chosen k. So the only thing left is to choose M, pass in an M, and then get some output. But there's another function in the same family, which is E of 1 comma M. This is the function where I chose k equals 1. So as soon as I choose k equals 1, I lock it in, I don't change it, and I get a function that instead of having 2 inputs, it only has 1 input because I already fixed k equals 1. And now I'm passing in n-bit inputs of plain text, and I'm getting n-bit outputs. And well, you see where this is going. There's another function in this family, which is 2. You can imagine that's like some sequence of 1s and 0s, comma M, and you get the idea. And so another way of thinking of this E function is not that it's a function that takes in 2 inputs and outputs 1 output. You can think of it as like a whole family of functions, and K varies in each of those functions. So what I'm saying here is, like, as soon as you pick a K, you lock it in, and as soon as you lock in the K, instead of looking at this whole family of functions, you've zoomed into exactly one of the functions where K is locked into your chosen value. And as soon as you use that one where K is locked into your chosen value, then you now have a function. You know k is equal to whatever your chosen value is. So your function now reduces to just taking an n bits of input and outputting n bits of output. Okay. Again, it's kind of a weird way to look at things. You can do the same thing with decryption. As soon as you lock in a k, instead of mapping two inputs, it just maps a single input to a single output. But the reason why we think about this, and I guess just for notation purposes, that's why I've put the k here as a subscript, because now I can write these as E1 comma n, E2 comma n. And now even if you look at the notation, it kind of looks like they're a family of functions, right? The first E, the second E, the third E, the fourth E, and the difference between each of them is just which key you're choosing to use. So that's why I've chosen to write it in this slightly funny way. But anyway, all of this is to say, E and D, instead of thinking of them as two inputs and one output, you could also think of them as a family of functions. As soon as you choose a k, it collapses down to a single input, single output function with a fixed k. Okay, all of that said, let's think about what happens if you fix a k. So let's fix a k. So on all of this slide, we've decided that we're going to use some k. I don't care what value it is, but this E sub k of m, it's only going to take in a single input m, and it's going to output some ciphertext. That's my fixed E sub k. And I can do this whole slide once for every single k that I can think of. Okay, so here's the idea. As soon as I fix a k, I now have a mapping of inputs to outputs, right? So if I say I would love, E of some sequence of bits, whatever, m. This is one of the functions in the family. It's not the only one, but it's one of them. Now what I can do is I can say, okay, I've already chosen k is 1240. I'm not going to change for my purposes for now. And in this m, I'm going to pass in all the possible 128-bit or n-bit inputs. So I'm going to pass in m equals 0, m equals 1, m equals 2, m equals 3. I'm going to pass in all the possible m's. And what I end up getting, if I compute all of those encryptions, is I get a mapping of inputs to outputs. So this is the input, it's the ciphertext, or it's the plain text. This is the output, it's the ciphertext. So I get a mapping. And so if we say n equals 2, which is what we're seeing on this slide, that means that there's 2 bits in the input. That means that for this particular function, for this particular key setting where I chose k equals 1240, you could have chosen something else. It looks like when I pass in 0, 0, it maps to 0, 1. So if I try to encrypt 0, 0 with this specific keyed function, not any function, but the one using this specific key, I get 0, 1. If I pass in 0, 1, I get 0, 0. Pass in 1, 0, I get 1, 1. I pass in 1, 1, I get 1, 1. That's the mapping that was inferred to me when I took all of the inputs, I ran them through the encryption function, and I drew arrows to what their corresponding output was. Okay. And so you can do this for all of the possible settings of E sub k of m, right? You can pick a k, you can draw these mappings. And so what does it mean for one of these functions to be correct? Remember, what it means to be correct is that if I take this input, I encrypt it, it better be the case that I can take the same key and decrypt it backwards, right? But like, look at this mapping over here. Is it the case that I can always decrypt a message? Well, let's see. There seems to be a problem with, you can think about, try and predict where the problem is. Seems like there's a problem down here, because when I took this particular function, there's a whole family, and I chose this one. Seems like when I passed in 1, 0 and I encrypted it with the key, I got 1, 1. Then I took 1, 1 and encrypted it with the key, and I got 1, 1. So what does this mean? This means that, well, suppose that I presented to you the ciphertext 1, 1, and I said, here's the key, here's the ciphertext 1, 1, please decrypt. Well, what's the decryption? Is it 1, 0? Is it 1, 1? Is it both? Is it neither? I don't know. It seems like what's happened here is that because 2 of the inputs map to the same output, if I then take that output and I ask you, which input or what was the correct input? I want to go backwards. I want to decrypt. I can't uniquely figure out what the original plaintext was. So that's a problem. And in math, what we're like, the mathematical way of saying this is that this function is not bijective because there are 2 inputs mapping to the same output. So the intuition here is that if I have 2 plaintexts and they map to the same output, that's what this expression says. It's exactly what we're seeing here. Then if I give you that ciphertext and I say, here's 1, 1, here's the key, please decrypt. You're like, oh, I can't, because 1, 1, it could decrypt to 1, 0, or it could be decrypt to 1, 1. I don't know which one you meant. it's not unique. So if the function is not bijective, we have this problem and we're stuck. Okay, so in order for this function to be correct, if I decide to map out exactly where the inputs to outputs are, it can't look like this picture on the left where there are two inputs mapping to the same output. It needs to be what we call a mutation or a bijection. And what that means is that each input should have exactly one unique output corresponding to it. Like, look at this one on the right. This is beautiful. We like this one because for each input, there is exactly one output. When you encrypt 0, 0 with a given key, you get 0, 1. That's it, right? There's nothing else mapping to 0, 1. 0, 0 doesn't map to two different outputs. It's exactly a one-to-one mapping. If I encrypt 0, 0, I get 0, 1. If I decrypt 0, 1, I get 0, 0. Beautiful. And this holds for all the inputs that I can possibly give. Okay, so that's what this slide says. We need bijections in order for our block ciphers to be correct. So whatever that E sub k is doing under the hood, it needs to be the case that if I pass in all the inputs, each input maps to a unique output. It's a one-to-one mapping. I can't have one input mapping to two different outputs. That would be too weird. I can't have two different inputs mapping to the same output. Then I can't decrypt. So one-to-one mapping is what I need for correctness. Okay, great. So I've at least proven or at least given a condition for what it takes for one of these E sub k of m's to be correct. Okay, and remember, if this is a whole family of functions, then this bijection has to hold no matter what k I plug in. So however you design this function, it needs to be the case that whatever k you plug in, you always get a bijection, right? The idea is you lock in a k, and as soon as you lock in a k, you can draw one of these pictures mapping inputs to outputs, or at least imagine drawing one of these pictures. And it needs to be the case that the resulting picture is a bijection, no matter what k you choose. If so, then this E algorithm that you've written, it's a good block cipher. Okay, that is our block cipher. Let's keep going. Let's think about, how do you know if this thing is secure? So let's think about security. Well, again, we can model security as a game. That's what we like to do. So I'll give you a definition that's kind of hard to read, and then we'll try and think about, is there a way to model it as a game that is easier to understand? So we already know that there's a whole family of functions, and as soon as you pick a k, what happens is you can write out the whole mapping of inputs to outputs, and that's your encryption function. So I'm like, Alice and Bob, we choose to use key 1240 or whatever. And as soon as they choose the key, they now have an encryption and decryption function that they can use. And the encryption and decryption function, it could be some piece of code, and it probably is, but you can also imagine it as being this bijection of inputs to outputs. Okay, and so when I know which function I'm about to use, I can use that function, and using that function, I can drop in all these arrows telling me which inputs map to which outputs, right? And so our goal is that wherever those arrows fall, it needs to be unpredictable. That's the intuitive idea. The intuitive idea is that whatever this E algorithm is doing, I have no idea what it's doing. It's probably running some code, but whatever that E algorithm is doing, it should, when I see 0, 0, it should map 0, 0 to something totally unpredictable. So 0, 0 to 1, 0, why? I don't know, it's unpredictable. Or like 0, 1 to 0, 0, and then 1, 0 to 0, 1. There doesn't seem to be any rhyme or reason as to where these arrows are falling. And that's what we want. We like that because that's going to be hard for attackers to guess. If these arrows fall in a really predictable way, then this block cipher is not secure because attackers can figure out where the arrows are pointing. And if they can figure out where those arrows are falling, they might be able to figure out, oh, given that this is the input, or given that this is the ciphertext, even if I don't know the key, well, maybe they can predict that the arrow came from somewhere else. We don't want that. So we want this thing to behave randomly. And in particular, we want it to behave so unpredictable that it looks random. So what do I mean by looks random? Well, what I mean by looks random is we want it to behave like this. So we already know that one way to drop all these arrows is to pick an E function, that's some piece of code, lock in a K. As soon as you lock in a K, you can run n-bit inputs to n-bit outputs. You plug in all the n-bit inputs, you get all the n-bit outputs, right? And that's your encryption. Okay. So, well, that's one way to draw one of these sets of arrows, is to pick the K, run all the inputs through E sub K, and then get all the outputs, and the arrows fall where they fall. That's one way to do it. But there's another way to draw these arrows, which is draw them randomly. So let's do that. This is another way of drawing the arrows. So one way of drawing them is to use the algorithm and run the code of this E function that was given to you. But a completely different way of drawing these arrows is to just pick them at complete random. So let's do that. All right, so here we go. And I'm going to flip my imaginary coin, or you can be my imaginary coin for me. I'm going to say, okay, 0, 0, it needs to map to some value. Let's do it randomly. Let's not ask E how to do it. I could ask E, I could pick a key and run it through the E function. I'm not going to do that. I'm just going to choose chaos. So 0, 0, it maps to any of these 4. Pick one at random. Okay, 1, 1. First one I heard. Okay, great. Now this does still have to be a bijection because we're looking for block ciphers that are correct, or we're thinking of the set of permutations, which means that we're looking for bijections, one-to-one mappings. So 0, 1, I need to drop an arrow. It can go to any of these remaining 3. Can't go to 1, 1 because that's not a valid bijection. So where does it go? 161 random number generator, go. 0, 1. Okay, arrow. Now 1, 0 has 2 more choices. What do you want?
0, 0.
0, 0. 2 people said it at the same time. Okay, so that's a really weird arrow. Okay, so that's my random mapping decided by referencing the CS161 random number generator. Okay, that's one possibility, right? And so what we are saying is that if it is the case that the set of arrows that fell out of the encryption function look exactly like, or they behave just like this completely random arrow drawing version that we saw here, then it is the case that this block cipher is secure. So, well, what do I mean by that? That seems kind of a weird definition. So I'm going to formulate it like a game because I think games and experiments are easier to think about than saying something like, oh, this block cipher behaves like a random permutation. It's indistinguishable from a random permutation. I think that's kind of hard to think about. So I'm going to play a game. So here's the game. Okay, you are Eve, like you always are. And so you're Eve, you don't know K because Eve doesn't know K. That's our assumption. So you are Eve, and I present to you 2 different functions, right? A function is some mapping of inputs to outputs. I present to you the one on the left, and I also present to you the one on the right. And I tell you, I came up with these arrows 2 different ways. So for one of these 2, I'm not telling you which one, but for one of these 2, I have my K, you don't know it, but I've chosen a K. I took the encryption algorithm with that fixed K. So I used E sub K. I plugged in the inputs and I got the outputs. That's how I drew the arrows for one of these 2, but I'm not telling you which one. For the other one, what did I do? I dropped the arrows in at random, just like we did together. And so as Eve, the person who doesn't know K, your challenge in this particular game is to tell me which of these 2 arrows or sets of arrows, which of these 2 functions is the output of E sub K for some chosen K, and which of these 2 functions is the one where I drop the arrows at random. Do you know? And if you don't know, in other words, you have no idea how to guess this with probability greater than 1/2, and you don't know K, right? If you have no way of guessing this with probability greater than 1/2, that means that our block cipher with some fixed K is behaving like a random permutation because its behavior from the perspective of you, someone who doesn't know K, it looks more or less random. Is it actually random? Well, not really. It's a piece of code that's systematically generating these arrows. But if it looks from your perspective like it's just total random arrows, and you have no idea where they're going, then it is the case that this block cipher, it behaves like random. And so Eve has no way of figuring out if the ciphertext is 0, 1, where does it point at? Eve has no idea because these arrows, they might as well have been dropped in at random. Okay, that is my long explanation for how you show whether a block cipher is secure. So the shorter version, the summary of all this stuff that I just babbled at you is that if it is the case that the inputs to outputs are unpredictable, given an input without knowing the key, I can't really predict where the output is, then the block cipher is secure. The way to make it formal and give it a game to formally define it is to say, if I show you the function and you cannot tell the difference between the function with a K and me dropping in the arrows at random, then it behaves like a random permutation. So from your perspective, guessing which input maps to which output is basically a random guessing game to you. So that's how it's secure. Okay, any questions about this? I know I've talked for a long time, so your turn to talk at me if you want. No? Okay, I'll talk some more then. So that's the distinguishing game. Let's think a little bit more about, well, there is one possible way you can break this. So, I'm not going to go into it in too much detail, but one possible way you can break this is, well, you could just try all the K. So you could say, okay, Well, I know one of these two came out of E sub k, and the other one was just dropped at random. And I'm not going to prove it to you, but the set of arrows that you get from dropping at random is way bigger than the set of arrows you get out of a fixed E function. So it's pretty likely that one of these two came out of an E function, the other one didn't, right? Or I know that for sure. And so what I could do, maybe that didn't totally make sense, sorry, but what I can do is I could just try all the Ks. So I could say, okay, you're telling me one of these two came out of E sub k. I don't know K, but all right, I accept your challenge. So I say, all right, I'm going to try E sub 1, and I'm going to draw the picture corresponding to E sub 1 and see if it matches one of these two. If it does, I know which of these two came from the E function, and I also know your key. Okay, if E sub 1 doesn't match any of these two, I go again and I try E sub 2. I draw the picture, I see if it matches either of these two. If it does, then I know which one came out of E. Okay, neither one. Okay, then I try E sub 3. So one thing an attacker could try is they could try a brute force attack. They could say, I'm just going to try all the possible Ks. I'm going to draw a picture for all the possible Ks and see if any of them match one of the pictures that you gave me, or one of these bijections that you gave me. And when I find one that matches, I'm like, aha. If I find one that matches this picture, I'm like, aha, this is the one that came out of E with a particular key, and this one is not. I could even try all the Ks and find out that I never get this particular set of arrows. Okay. So we could do that. That's a possible way to break this. And if you do that, what's the probability that you win this game? 100%, because you can always figure out which of these two is coming out of E and which one's not. However, how long would that take? Well, let's try plugging in something that people use in real life, which is people tend to use K equals 128. It's pretty common. And so that means if K is equal to 128, how many different E's do we have to try? We have to try 2 to the 128 possible E's. Is that big? Yeah, that's really big. It's so big that it's going to take, and there's all this math to prove it. I'm not going to walk through it. Turns out if you want to try all 2 to the 128 different possible Ks, we would be here until like the sun like burns out. Okay, so I don't know how much time that is, but it's like astronomically long. By the time you're finished trying out all the possibilities of this 128-bit key, like the universe will have collapsed, or like the sun will have like swallowed the earth. I don't know. Like astronomical level things will happen. And so we don't have to worry about it. So yes, technically there is an attack on this scheme where an attacker can distinguish, but it would take so astronomically long that it is not something that we need to concern ourselves with. Okay. What if you are worried? You're like, okay, but what if my thing is so secure that it needs to be secure even if the sun swallows up the earth? Okay, fair enough. Then you can upgrade to a 256-bit key. And now, I don't even know what this is. This is like astronomically long. So it's like, even if after the sun collapses, you're still not even close. Okay, I don't know what this is. This is like, my brain's going to like collapse into a black hole thinking about these numbers. So I'm not going to worry about it. So in general, even though brute force attacks are possible with block ciphers where you try every key, as long as you use a reasonable key size, which in today's terms is 128 bits or 256 bits or anywhere in between, it's going to be the case that nobody's going to have a shot at brute forcing it within like the lifetime of the universe. Okay. So that's what this slide says in a lot of words. Okay. So we figured out block ciphers. We know that how they're correct. They need to be a bijection. We figured out how they're secure. The bijection, the arrows that pop out of the block cipher, need to look random for a given key. So how do we know if they're efficient? Again, there are ways to prove this. We're not really going to go through it. But the key behind block ciphers to make them efficient is, well, if you think about the inputs to block ciphers, they're ones and zeros. There are a lot of bits. And so how do you implement this block cipher? There's a lot of different block cipher algorithms out there, but almost all of them, they tend to use things that are cheap. Like XOR is really cheap on a modern processor. And that's like a 61C topic. So I'm not going to talk about it in huge detail. Or like bit shifting is really cheap. Looking up values in a small table. These are all really cheap operations on modern processors. And so in general, block ciphers, the amount of time they take from our perspective in like a modern world, basically insignificant. Okay. That's all this slide says. So yes, you could certainly decide, you know what, my block cipher is going to take the bits and it's going to compute this like super complicated mathematical formula. Like sure, but that could take a lot of time. Modern block ciphers, they tend to use things that are really cheap, like repeated applications of XORs, bit shifts, like little lookup tables, because those are fast. And we like fast. Okay. So I told you all about block ciphers, this category of functions. I have not told you what goes in the E box. I've also not told you what goes in the D box yet. So let's figure out what goes in those boxes. Well, there's a lot of different things you can put in there. And so one of the first ones that people used was something called DES. This is obsolete now. And I mean, one of the reasons why it's obsolete is because the key is 56 bits. And even though 2 to the 128 is astronomically big, 2 to the 56, maybe some supercomputers can handle that. So this is the older version. People don't use it anymore, but it is here. One thing on this slide that's kind of interesting is that the National Security Agency influenced it. So who knows what secrets they snuck in there. But anyway, that's the DES. People don't use it anymore. And so around like the 1990s or so, people kind of realized like, okay, this thing, it's getting kind of old. Computers are catching up. 56 bits is not enough. And so they needed to design a better block cipher. They needed a better algorithm to shove in that little E box to compute encryptions and decryptions. So here's what they came up with. What they did is, well, they had a race. And so they opened this up to the security community and they had this big old competition, and whoever won became the one true block cipher standard that everybody in the world would choose to implement. And one thing that's kind of funny is that one of the finalists, there were 5 finalists out of hundreds of submissions, and one of them was actually co-designed by David Wagner, who teaches, I think, Data 8, taught 161 a couple times. I worked with him before on 161. So pretty cool. If you ever see him around, ask him about two-fish, and I'm sure he'd be happy to talk about it. That's the fun side. So go Berkeley. The sad side is that he lost, so he didn't win the competition. But hey, I'd say one of the 5 finalists for the encryption standard that the whole world uses is pretty good. I'm never getting there, so that's pretty good. But anyway, the takeaway is that what they ended up choosing was fast for all platforms. It was something that they thought was secure, and that became the Advanced Encryption Standard, or AES. So the name during the competition phase, they called it Rindell. I think that was the person who invented it, maybe. But once it got adopted and it won the competition, now everyone just calls it AES. Okay, so here's AES. This is the thing. This is the algorithm that went inside that box. And even though you can put lots of different things inside there, like if you feel like it, big Berkeley fan, you can go take Dave Wagner's two-fish and shove it in there. But most people in the world, they use AES, which is the Rindell algorithm. And this is what it looks like in the high level. There's actually different versions of this algorithm depending on what key size you like. So pick your favorite key size. There's an AES 128 algorithm, AES 192, AES 256, depending on the size of your keys. Okay. Most people, 128-bit keys is enough. If you are astronomically paranoid, go use the 256-bit version. That's all right. The block size is 128 bits. And so when this algorithm was designed, it was designed for specifically 128-bit inputs. That means that you cannot pass in, n equals anything else. N is fixed at 128. There are 3 versions of this algorithm fixed with k equals 128, 192, 256. That's it, nothing else. Okay. Now, how does this thing work? Well, it's pretty complicated. It's a lot of shuffling. I will show you how it works, although the slides are all blue, so you don't have to know. But as you can see, it's like the 2 takeaways that I have from these slides are, it is complicated as heck. I don't know what half of this stuff is. And, that's one takeaway. The other takeaway is that all the operations are pretty cheap. They're all XORs or shifting bits around. There's no ridiculous mathematical algorithms here. We're basically, you can almost think of what we're doing here as we're taking the input and using the key to shuffle things around in a way that we hope is deterministic and hard for an attacker to guess. So for example, here we're swapping bytes around. We take the bytes, we form a little grid, and then we just decide to swap that one and that one. I don't know. Okay. And then, we decide to swap some more, and we shift these over and shift those over. And it doesn't really matter how these work exactly. But the idea is that with these repeated shifting inputs and outputs, ultimately, what you're going to do after all these, more cycles and more mixing, right? And so ultimately, what you're going to do, right, is you're going to have all those M's, as we saw from before. And this algorithm, what is all this shifting doing? When you're shifting and you're mixing rows, I don't even know what that means. Right? But when you're doing all this XORing and shifting and mixing, the ultimate goal is just to take in some bit of inputs and decide which output it maps to. So your ultimate goal is just to decide that arrow. And if it is the case that deciding that arrow happens in a very unpredictable way, then your AES algorithm is secure. That's all that we're saying here. Okay. There's more. Okay, I'm not going to talk about this. As you can see, it's a lot of stuff. So one funny thing I will say, though, about AES is that it has actually not been proven to be secure. So we already saw from before that if I can play that game where I give you a box, or a permutation, a picture of arrows, and I say one of these was computed by taking AES, the AES block cipher, so maybe something like that. And I chose a specific K. I didn't tell you which one, but I chose the K. I plugged in all the M's and I drew the picture, I drew the arrows and I handed it to you. And I also gave you one where I drew all the arrows at random and I want you to know which is which. And if I can prove that no matter what you choose to do, you cannot distinguish, then it's secure. Turns out for AES, there's actually no proof for it, which is kind of funny. However, it's been 20 years since it was invented and nobody has even come close to breaking this thing. The way that these bits are shuffled is just too unpredictable for anybody. And so nobody has ever figured out how to deduce patterns from it. As far as we know, the arrows and the places that they drop in are more or less unpredictable. Okay. I guess since I've said this word unpredictable and random a lot, I will briefly mention that when I say that those arrows are dropped in unpredictably, it does not mean that you cannot decrypt messages, right? So like if I say, oops, that's a really weird squiggle. So if I say, like I want E sub K of M and I've chosen some certain K, and we've seen this picture over and over again, okay, just to be clear here, right? When I choose E sub K and I plug in all the M's, and even though these arrows are dropping at random, so even if I'm using AES, you have no idea where those arrows dropped in. Once I fix this, like it's fixed, right? So as soon as I encrypt something, it moves to some, or it maps to some output, and I can still decrypt the output, right? So I am not, once I drop in the arrows at random, they're fixed for this particular E sub K. So it's still decryptable. It's still a bijection. It just so happens that the way that I drop in the arrows is super unpredictable. That's what makes it secure. Okay, that's AES. That's what people use. It's one of many block ciphers, but it's the one that won the contest, so that's what we use. Okay. Great. So are we done? Well, let's take this AES block cipher and let's run it against, so far we've been running experiments that, like for the one-time pad, we ran it against a variant of this experiment. It wasn't exactly this, but you know what? This slide even tells me no one's broken it for 20 years. I'm feeling pretty good about AES. So I'm going to shove it into the in-CPA block cipher game, or the in-CPA confidentiality game that we did from last time. I'm feeling pretty confident. I'm going to take this block cipher scheme and we're going to play the game together. And let's see if block ciphers are secure. Okay, so here we go. Let's do it. So we're going to play the game. So I'm Alice, you're Eve, as you always are. And so here we go, right? As we said from last time, because you have the power to trick me into encrypting things, you're allowed to before and after the challenge phase. Right? You can always tell me, hey, please encrypt this, and I will always faithfully encrypt it for you. What function am I going to use? I'm going to use E sub K. That's the function I'm going to use. Okay, so here I go. You're going to have to trust in me and believe that I'm doing this for real. So I'm going to say E sub K, that's the AES block cipher. I can't run AES in my head, unfortunately, but I'll try and simulate it the best I can. So I'm going to choose a random K. You have no idea which K I chose, and I've locked it in. Okay, so E sub K of M. I've chosen a K. That's my block cipher. I'm sticking to it. And I know that if I take this block cipher and I run it on all the possible inputs, today we're using 2-bit inputs, but you can certainly do this for much larger ends. In fact, in practice, these would be 128 bits. There's some arrow mapping corresponding to my E sub K. I'm not going to show it to you because it's my encryption algorithm and you don't know K, so you don't know where the arrows are, right? It could be anywhere. Okay, but that's my mapping. So I'm not going to show it to you, but you are now allowed to ask me for encryptions. And as soon as you're done, as soon as you're confident, you can then ask me for, you can then send me M0 and M1. I will flip a coin and encrypt one at random. And then you will get another chance to ask me for some encryptions. And then you're going to guess. Okay, so let's do it. So I'm feeling pretty evil, so I'm going to not let you do this. In theory, you certainly could, but turns out you don't need to. Eve is pretty smart in this one. So I'm going to, even though you are technically allowed to do this, I'm going to skip to the challenge phase just to save ourselves some time. So we are going to start here. And technically, before this started, you could have asked me for a lot of encryptions, but in the interest of time, we're going to start here. So you must provide to me 2 messages, M0 and M1. Okay, M0 and M1. And this time we're going to use bit strings. In real life, these would be 128 bits, but in this example, we're going to use 2 bits because my slide doesn't fit 128 bits. Okay, so what do you want M0 to be? You have 4 choices. It's a 2-bit message. What do you want? Anything? I realize it's not the most exciting of choices, but you got to pick one. 1, 0, right on. Okay. And M1, you need to choose a different one. Remember, these have to be different messages. So pick another one. What do you want? 1, 1. Okay, sure. So there they are. Okay. You've chosen your messages. You've locked them in. So now it's my turn. I'm going to, turn around. You can't see me. I'm going to flip my secret imaginary coin. And I have randomly chosen one of these 2 to encrypt. You don't know which one. And I'm going to give you back C. And I'm going to tell you that I encrypted 0, 0. Okay. And you have no idea. 0, 0 could be the encryption of 1, 0 or the encryption of 1, 1. You don't know because you don't know K. If you knew K, you'd know exactly where my arrows fell and you'd know which one I encrypted, but you don't. Okay. So onwards we go. We go down here to this phase. And in this phase, you are now allowed to ask me for the encryption of anything you like, right? And I'm going to have to faithfully encrypt it with a key for you. So you can ask me for the encryption of anything, and I will faithfully give you the answer. Okay, so it's all yours. What do you want to do? You're trying to win this game, right? Right? What do you want? You want 1, 0? Okay. You sure? You don't want anything else? You have to take 1, 0? Okay, I'll give you 1, 0. So the encryption of 1, 0 is that. Okay. Satisfied? Want anything else? You want 1, 1? You sure? You really don't want 0, 0 or something? You really want? Okay. Okay, I'll give you 1, 1. So unfortunately, I have no choice. You have the power, right? So you're telling me to encrypt 1, 1. I have no choice but to take my key, faithfully encrypt 1, 1, and okay. Now are you happy? Want anything else? Or do you think you're ready to guess B? Okay. Seems like no one else wants me to encrypt stuff. So now it's your turn to guess B. So to summarize what has happened, right, you have provided to me 2 messages, M0 and M1. I turned around, flipped a coin, I encrypted one at random. I did not tell you which one I encrypted, but I did tell you that the encryption was 0, 0. And then I allowed you to ask me for the encryption of anything you wanted. You asked for 1, 0, and I faithfully encrypted it. You asked me for the encryption of 1, 1. I faithfully encrypted it as well. Now it is your turn to guess. Okay, Eve, don't let me down. How many people think I encrypted M0? Nobody. How many people think I encrypted M1? Many people. Okay, so now I reveal to you what M I chose, and indeed I chose M1. So you win this time, but I'll get you back next time. Or will I? Because if I run this over and over and over again, you could probably use the same strategy on me over and over again. So just to clarify what happened for those of you who didn't guess M1, but don't think there's anyone in person, but you never know. What happened is, now I can reveal to you, I don't know what key I chose, but it seems like I chose to map 1, 0 to 0, 1. I chose to map 1, 1 to 0, 0. And the other 2, don't think it really matters. Okay, but basically what happened here is that this block cipher, once I locked it in, it was what we call deterministic. When I encrypt the same thing twice, I get the same output twice. We saw that here because I chose to encrypt M1. And when I encrypted M1, I guess I've been using E here, sorry. When I chose to encrypt M1, I got 0, 0. Okay, that's what this is. And then you asked me to encrypt M1 again down here. And what did I do? I went to my mapping of arrows, right? As soon as I picked the K, the arrows are locked in. I chose 1, 1. I looked, oh, the arrow points at 0, 0. So I gave you 0, 0 again. So in other words, you exploited the fact that when I encrypt something twice, I get the same output twice, and you won this game. And it turns out, if we do this over and over and over, you're going to win every single time because all you have to do is ask me to re-encrypt the 2 messages and see which one matches. You could even just ask me to encrypt one of them and see if it matches or not, and then deduce from there. But the whole takeaway from this whole slide, which I will now give to you in slightly nicer handwriting, which is that as Eve, you can always win the game on block ciphers. And that's because you're leveraging the idea that if you ask me to encrypt the same message twice, I will always output the same ciphertext. Nothing in this is changing as soon as I pick K. Okay, so all of this is to say, because Eve always wins, block ciphers by themselves, not NCPA secure. We went through all the trouble of designing this thing, and we said, well, look, no one's been able to break it. But at the end of the day, Eve still won, using this power of asking me to re-encrypt stuff. Okay, so how am I doing on time? Let's reflect on what we learned. This will probably spill into next time as well. That's okay. So we learned that block ciphers are not NCPA secure. And the main flaw that allowed you to win this game, to be clear, is that this game was deterministic. When you encrypted the same, or when you ask me to encrypt the same thing 5 times, you will get the same output 5 times. So when I encrypt something mysterious, M0 or M1, all you have to do to figure out what I encrypted is to ask me to re-encrypt the same messages twice. And it turns out that any scheme out there that has the same property where you encrypt the same thing twice and get the same output twice will always fail this NCPA game. It didn't have to be block ciphers. Any scheme out there that has the same property where you encrypt the same thing twice and get the same output twice always loses this game, because Eve can always pick the same strategy, which is in this phase down here, ask to re-encrypt M0, ask to re-encrypt M1, see which one matches. And she knows there will always be one that matches, because when I re-encrypt M0 and M1, I get the same encryptions out. Okay. So that means that any deterministic scheme fails this game. And if you think about this game as a model, that's a good thing, right? Because if a scheme is deterministic, what is our ultimate goal? Like, let's zoom out and think about the big picture. The ultimate goal is confidentiality. We want it so that when you encrypt something, the attacker has no idea what you encrypted and they can't learn anything about what you encrypted. However, if you use a scheme that's deterministic, then the attacker learns something, right? Because if I send a bunch of ciphertext over the channel and some of them are the same and some of them are different, the attacker knows, ooh, Alice is sending the same thing right here. And now she's sending something different. And now she's sending the same thing as what she sent on Tuesday. So if you use a scheme that's deterministic, you are leaking information because you're telling the attacker, or you're giving the attacker signals when you're encrypting the same thing twice. We don't like that. So it is a good thing that deterministic ciphers fail this game, because it means that deterministic ciphers don't pass our confidentiality test. And that's what we want, because we think deterministic ciphers, they're not good. They allow the attacker to find out if, hey, the thing that Alice sent today is the same thing as what she sent last Tuesday. That's bad. We don't want that. So it's a good thing. It's intended. It's like built into the system that games or ciphers that are deterministic, they fail the NCPA game. Eve can win. So that's one issue, which is after all this trouble, we still don't have something deterministic. Okay. What else? Well, another problem is that these things don't even encrypt messages of a fixed or of longer messages, right? We already said that the AES block cipher as designed, all those bit shifting things that we saw from before that were super complicated, they only accept messages that are exactly 128 bits. So if your message is 127 bits, like good luck, right? It's not going to happen with the block cipher. Or if your message is 129 bits, you're out of luck. Block ciphers do not accept those inputs. You're passing in an input that block ciphers do not support. So it's not going to work, right? So block ciphers, they're good. They're a nice building block, and we're going to see how to use them to build something better in, I guess, the last 10 minutes of today and a lot of next time. But block ciphers by themselves, they don't do what we want. So that's unfortunate, but we can use them as a building block. So that's the end of block ciphers. And then I'm going to start trying to build something better out of it, if there are no other questions on them. Yeah. If you're not NCPA secure, how does Eve win? Remember, if Eve is the adversary. Oh, how did the block cipher win this competition if it's not NCPA secure? So that's a good question, right? And so remember, there's 2 different definitions of confidentiality that we're working with here. So for the block cipher, we decided that the definition of a good block cipher was on this slide. The definition of a good block cipher is this, right? And this is not the same thing as confidentiality. This just defines what makes a block cipher good and what makes a block cipher bad. And we decided that block ciphers are good if the arrows fall in an unpredictable, random-like way. And so this thing won the competition. All the finalists were good because all of them dropped the arrows in a random-looking way. But just because it passes the test to be a good block cipher does not mean that it passes the test to be a fully, where's the slide? it doesn't mean it passes the test to be a fully in CPA confidential scheme. So that's the difference. That's a good question. There's a difference between what makes a block cipher good and the fact that block ciphers do not pass our definition of confidentiality, right? There's different definitions, depends on your threat model. Okay. More questions? Yeah.
It's like the course of time, you trying to figure out B equals A.
In this scheme or in general?
Yeah, is Eve trying to figure out here?
Yeah, so the question was, what is Eve trying to figure out if Eve were to try a brute force attack? Well, Eve is in general is just trying to figure out something about your scheme, right? And trying to break the confidentiality of your scheme. So on this slide, Eve is trying to figure out, her ultimate goal is to figure out B. But if it is the case that Eve figures out something about K, maybe she figures out the exact value of K. If Eve can figure out the exact value of K, that could help her learn B. So Eve's ultimate goal is to get better at guessing B with better than 50% probability, but how she gets to that is up to you. She could do it by learning something about K. She could do it by exploiting something that's really vulnerable about the encryption algorithm itself. She could do it by just getting really good at guessing B equals 0 or 1, or picking special M0 and 1. So the strategy is up to you, but the ultimate goal is to get better at guessing B on this slide anyway. It's a good question though. Okay. That's our building block. So let's try to use this thing, award-winning block cipher. Let's try to build something better. Okay. So we already saw it works. It has this nice security property. We want to use this as a building block, as we said from before. This is a great property. The fact that those arrows are random, that's really powerful, but by itself, it's not enough. So we need more. We need that with more stuff to build something that is truly in CPA secure. So we're going to take those block ciphers and we're going to chain them together and combine them to build what we call modes of operation, which is some fancy term for making them better. Okay, I guess we'll do one today and then we'll do maybe a bunch more next time. There's 3 in total I have to show you. Okay, here's our first one. So we'll design it together. This is the block cipher. We've seen it before. It's our old friend. But remember, there is a problem. This input is forced to be exactly 128 bits, no more, no less. If you pass it anything else, the block cipher will simply complain and say, that input is not valid. I refuse to encrypt this thing. Okay, well, that's a problem. So say your message is 256 bits. Okay, well, if it's 256 bits, what's our move? Well, one block cipher is not going to do it. So you can try and think about and predict my next move. My message is 256 bits, and one of these things encrypts 128 bits. You know what? I'm just going to pull out a second block cipher. Now maybe I can use this to encrypt 256-bit messages. So how would I do that? Well, I would take my message, which is 256 bits. I would chop it in half. That first half, the first 128 bits, I'd pass it through a block cipher with some fixed key. The second one, I'd pass it through some block cipher with a fixed key. But in both cases, I would get some ciphertext. And once I combine it, I get my resulting 256-bit ciphertext. That's my first attempt. Is it good? I guess we'll find out. A couple of things I will note is that we could have chosen to use different keys here, but we chose to use the same one. Why is that? Because remember, what was the whole point of block ciphers? Why did we go from, or why didn't we just quit at one-time pass? Why did we have to go through all this trouble of building block ciphers? Because we would like to be able to encrypt long messages and repeated messages with the same key. I don't want to have to keep coming up with keys. It's expensive. So in this case, I have chosen to use the same key for this encryption. That's what this slide says. Okay. So, well, we are done. We've already invented our first mode of operation, just like that. And this mode, all we have to do is say, if your message is too long, chop it up into smaller pieces, take every piece, pass it into each of these little encryption blocks. Use the same key every time because I don't want to have to think of coming up with different keys. Every single time I get some ciphertext out. Remember, what is this encryption block doing? It's taking the plain text. It's using that big lookup table. Right? It's really executing code, but you can think of it as that big lookup table that has all those arrows that are unpredictable. You find the arrow, you follow it, you get some ciphertext output. We do it over and over again for each chunk of plain text. And then at the end, we take all the ciphertext blocks, we mash them all together, and we get the resulting ciphertext. That's a possibility. If we do that, we get this thing as a fancy name. We call it ECB for short. Here it is in equations. And really all you have to do is take the resulting ciphertext and put them together. That is a concatenation operator. So you just take the bits, smash them together. And that's it, side by side. And so, yeah, that's basically the algorithm. So are we done? Well, can we go home? Well, you can go home in 6 minutes, but we can't go home yet because this thing is also not NCPA secure. And why am I telling you this without even showing you a proof? What's your one word answer for why this thing can't be? There's just simply no possible way that this thing could win the NCPA security game. Deterministic, exactly. It has to be the case that this thing, Eve will always be able to win using the same strategy as before. Because if I encrypt the same thing twice, I get the same output twice. This block cipher, even though the arrows fall in super unpredictable ways, overall, the block cipher itself, it's still deterministic. Once I lock in those arrows by choosing a key, if I pass in the same input twice, follow the same arrow, get the same output. Still deterministic, still a failure. Okay, so in case you're wondering, well, this deterministic thing, when you say, okay, well, maybe the attacker can learn when I have a message and I encrypt it and it matches the message from before, I can kind of see how that's bad, but is it really that bad? Well, here's a picture that shows you how bad it could be. So what I'm going to do is I'm going to take this image, it's an image of the Linux penguin, I believe, and we're going to encrypt it. So the way we're going to do it is we're going to use ECB mode. And the way that we're going to do it is we're going to take every pixel. So you can imagine this penguin is it's a grid of pixels, right? And each of these pixels, I can represent it as a sequence of ones and zeros. Like this pixel is colored white, that pixel is colored black, that one's colored orange or whatever. I can take each of these pixels, turn it into ones and zeros, and encrypt it. And that would be ECB mode because I'm taking each individual pixel, like this is pixel 0, this is pixel 1, this is pixel 2. I'm passing each one through my block cipher encryption with the same key, and I'm getting some output. So try and predict what will happen as soon as I do the ECB encryption on the penguin. And remember, if I pass in the same input twice, if I encrypt the same pixel twice, I get the same output. That's the key of ECB. That's the key of all deterministic schemes. When I pass in the same input twice, I get the same output. Okay, so this is going to reveal to you what happens when block ciphers are deterministic. So we encrypt the penguin, and we really want this to be confidential. We don't want people to know this is a penguin when I encrypt it and send it over. So I encrypt it, and I really hope people don't know this is a penguin, right? But we can look at it, and we can probably guess. So what happened here is that any 2 pixels that were white, right, they got an encryption that was the same. Any 2 pixels that were black, they got an encryption that was the same. There's a little bit of image artifacting that's kind of funny, but still pretty penguinish to me. So this is the problem with deterministic schemes that we have to deal with. We don't like this. Okay. And another problem with deterministic schemes is that if I took this penguin and I encrypted it 10 times with ECB, I get the exact same image out every time. Also not good. Okay, so block ciphers are deterministic. That is what caused the penguin to appear. And ECB itself is deterministic. That's what causes you to get the same penguin every single time if you encrypt this 10 different times. Okay, that's ECB mode. So before you go, I guess I will give you a really brief preview of what we're going to start doing next time. So what we're going to start doing next time is we're going to start adding randomness. And one thing I will note just before we get there, right, we're going to do it in more detail next time. But one thing I want to note, because super common, maybe the most common thing people mess up in this unit. So I'll say it over and over again. So I want you to hear it first time today, and then you'll hear it 10 more times next time, is that adding randomness does not guarantee that your scheme is NCPA secure. I'll say it one more time. Adding randomness does not guarantee that your scheme has confidentiality. Okay. It is true that if you have 0 randomness, the whole thing is deterministic. There's no confidentiality. We already saw that with the penguin. You play the game and you won over and over. You win every time. So if there's no randomness, it's not NCPA secure. However, just because you added some randomness does not mean that your scheme is NCPA secure. Randomness does not give you confidentiality for free. You have to use randomness in an intelligent way to actually get confidentiality. And just to hammer it in one more time as you quietly pack up, right? Imagine if I took ECB and I said, you know what? I'm going to make ECB random by adding a block of random bytes at the end. So here are some random bits. So my ciphertext now is this whole thing plus the random bits. I added randomness, but is this scheme secured? Well, no, because this entire section is still not secure. I just added some garbage at the end that's random. So that didn't make sense. Don't worry too much about it. But the key takeaway that I want you to hear now before you hear it again next time is if you add randomness, you do not get security for free. You have to use randomness in intelligent ways. So what we're going to do next time is try and build randomness in more intelligent ways. Okay. I realize I am slowly falling behind, but we will make up for it. There's some buffer in the lecture, so don't worry about it. And I will see you on Wednesday. Okay, take care, y'all.